This video is about graphs of logarithmic functions. Now that we've been understanding the definition and some practical use of logarithmic expressions and functions, we're going to take a look at how their graphs relate. Let's recall a couple things. First of all, logarithmic functions are inverses of exponential functions. That's going to help us out to realize. Secondly, inverse functions graphs are symmetric about the line y equals x. When we were discussing inverse functions a while back, that was one of the tenets of them, and so we're going to bring that into play as well. Visually speaking, if I want to find the graph of f of x equals log base a of x, and we recall what we just mentioned about inverses, then we'll find it very convenient to understand the symmetry about the line y equals x. So on a graph here, I'm going to go ahead and put in a dashed line of y equals x, and then understand that the function y equals log base a of x, which is what we're trying to graph here, is symmetric about that line when compared with y equals a to the x. So these are inverse functions, and notice if I were to fold my paper on the dashed line y equals x, then one of these curves would land right on top of the inverse if you were to, again, kind of fold across that line. That's what it means to have symmetry about the line y equals x. Notice that along with that, the point 0, 1 was a y-intercept for an exponential graph, as we saw previously, but then the point 1, 0 is an x-intercept for a logarithmic graph. So that goes in line with the symmetry that we're talking about here, and we'll come to use that as we try to graph some of these. Now with logarithmic graphs, along with all the things that come with being inverses of exponentials, we're going to find even more than just the symmetry, that the asymptote is different. So as you may recall, with an exponential function, there was a horizontal asymptote right on the x-axis. Well, now, symmetrically, with a log graph, there is a vertical asymptote right on the y-axis. So I'll put a dashed one here in blue, and that will bind our graph to be stuck to the right of it. And that affects lots of things. So first of all, for the vertical asymptote, we're going to say that starts as just x equals 0, and that can shift depending on, if there are any transformations that move left or right, that vertical asymptote would move with them. But the parent function domain of a logarithmic graph would then be 0 to infinity, but with a parenthesis on 0, because you can't actually hit the vertical asymptote. So our graph plummets down toward the asymptote, chasing it downward forever, but never quite gets to it. The range, though, of a logarithmic graph would be all real numbers, negative infinity to positive infinity, and actually that's consistent with what we were expecting. With inverse functions, their domains and ranges are switched, and if you look back at the domain and range of an exponential function, you'll find that these are opposite for log graphs. So at least that's consistent with what we might be expecting. Also note that all transformation principles, which we've done now with various functions, apply to logarithmic functions. For example, if I had y equals log base 2 of x minus 4, then the minus 4 that we see grouped in with the x would actually shift the graph to the right by 4 units, as we've been seeing with transformations by now. We know that would happen with other various graphs, and when we see a log graph, it's no different. Or secondly, suppose we had y equals 1 minus log base 10 of x. Well, here you'll notice a couple things. First of all, there's a 1 up front. Now remember, that's a positive 1 that's being added to the function. It might as well be at the end of the function as a plus 1, but either way, that value shifts the graph up 1 unit. And then also notice there's a minus sign in front of the log. That'd be like a negative sign way out in front of a function, and we've been seeing that a while now. That will do a vertical reflection. And so those two transformations would occur where you can still see the parent function evident by the base. So our first example was log base 2 of x minus 4. That means log base 2 of x would have been the base or parent function of that. In the second example, y equals 1 minus log base 10 of x. Again, log base 10 of x would have been the parent function in that example. Let's also note that a vertical asymptote shifts left and right with the function visibly. This affects the domain of the function. Though it does shift up and down with the function, this movement is invisible since it is vertical. So if you look back carefully when we defined exponential functions, you'll find this to be correspondingly opposite with it, right? So exponential functions had a horizontal asymptote. Notice logarithmic functions have a vertical asymptote. And that would make sense given the inverse symmetry about the line y equals x. Let's consider an example where we want to graph the function by identifying and graphing the parent function using a dashed curve, and then use transformations to graph the function with a solid curve. We also want to state the domain and range of the function. This first example reads f of x equals log base 2 of x minus 3 in parentheses minus 4. So let's identify several things, including what the parent would be for this function. Remember, we keep the same base, which is defined as a base 2 here. So for our parent function, we'll say this is just log base 2 of x. Notice the parent function has none of the bells and whistles that would move or shift or slide or shrink or stretch. None of the transformations show up in the parent. So with having just a y equals log base 2 of x, we want to start by graphing that with a dashed curve and then adjust it. Now let's also recall that these transformations will occur. The minus 3 inside the parentheses with the x minus 3, that will move the graph right 3 units, and then the minus 4 that's on the end will take the graph down 4. And so we'll be sure to make those adjustments as we go. But let's start with the parent function first. Now with a parent of y equals log base 2 of x, it's actually a little tricky to try to go right from that even simple parent function to a graph. We'd rather utilize what we already know about exponentials and make an xy table, but convert the parent function to exponential form. It's just much easier to think that way with what we're used to. To convert this, we'll take the base, which is 2 for log base 2, and write that base to the power of the value that's on the opposite side of the log, like we've been doing. So 2 to the y equals, and then it'll be equal to the input for the log, which is the x. So 2 to the y equals x is synonymous with our parent function being y equals log base 2 of x. That's just going back and forth with the definition of logs that we saw earlier on. And we can use, I think, the more familiar exponential form of it to make a table more easily. What I mean is, let's just go ahead and actually pick y values here. So like, what if y was 0? Well, 2 to the 0 would be 1, so x would be 1. Okay, or let's pick y to be 1. 2 to the 1 would be 2, so then x would be 2. It's just easier to work in the territory of exponential equations, so I think it's a good use of what we know to go that route. Now, once you get a couple points, remember, we already recognize, hopefully, the shape, the general shape of a log function. Now that we have a couple points to plot, let's go ahead and put those on. So we have 1, 0, that's our x-intercept, and then we have 2, 1. Now, let's also recall that the parent of a log function will have a vertical asymptote. So I'm going to put that one in, of course, dashed. I'm going to keep that one in blue. We'll do the final one in red, like we've been doing with the definition. Okay, so we have a blue vertical asymptote. Remember, it starts right on the y-axis for the parent function of a log equation. And so that's where we'll put it. Now, also recognize the general shape. And so we're going to go with a dashed curve, connecting the points we've already put on here, and using the general shape of a log graph, which is a curve that plummets downward toward chasing the asymptote downward that's vertical there. But then it increases, but kind of slowly leveling off as x values increase to the right. Now, that's our parent function graphed with a dashed curve. We also would like to recognize the transformations, though, that we've already seen in the equation. We have to go right 3 and down 4. So since we have a couple points plotted already, we'll just do that with those points. If I take the point 1, 0 and go right 3 and then down 4, the new coordinate will end up in its place. Same thing with the point 2, 1. We'll go right 3, down 4, and the new points will show up in the exact same orientation. Notice when you're just shifting left or right, up or down, the picture looks about the same, just moved over. Now don't forget that with a log graph, as we've already stated, we have a vertical asymptote, and as we mentioned in our notes, when you move right or left, you can actually see the vertical asymptote moving. So if we went right 3, we're going to have a new asymptote that's moved now 3 units to the right. We'll now go ahead and put this final vertical asymptote in a solid red, or a dashed red line vertically. So it's really the line x equals 3, which is a vertical line. That's the final asymptote. Then, as we've already graphed our points that are translated right and down, we now want to connect them to form a solid curve graph, which will be our final graph. And it will mimic the shape of the parent function, but now it's bound by the vertical asymptote, and of course it uses the new points. Now we also want to state the domain and range of this function, so let's do that by understanding the domain. That's all the x values. That's adjusted when we move right 3 and the asymptote moves. Notice we're stuck to the right of the asymptote, wherever it is, and ours ends up at 3, which means our domain is anything after 3. So we'll say 3, infinity in interval notation. And then the range for any logarithmic function would be all real numbers, so we'll say negative infinity to positive infinity, and that would do it. So we have our domain and range and our parent and final transform function showing up on our graph.